Alright, so as promised before, here's a relatively quick tutorial on how to use Simscale to run finite element modeling on the example of a violin bridge in this case. But of course, it's a general software tool. You can use it for whatever you want. First thing, what is Simscale? I'm not affiliated with them in any way or something. I'm just showing you a tool that I think is really useful, and for our purposes, it's free. It's not generally free, but for small scale simulation, you get so many free simulation hours that it doesn't really matter. So Simscale runs in your browser. As you can see, I just have Google Chrome open here, and I went to simscale.com, and I already logged in with my account. So you will need to make an account. I'm not showing that process here, just we're starting from this starting page with a logged in account, and you get a set number of simulation CPU hours. So they are running this on CPUs, and a number of hours that they have to calculate stuff is given to you in the beginning. I believe it's 5,000 hours, and so calculations for which maybe take 0.01 hours to 0.05 hours or something. So you could run a lot of calculations for free on this service for small things like violin bridges. All right, so we're in the dashboard of Simscale, and I'm gonna go to my projects, which I can go to via this button as well. It's going to my dashboard, so we could also navigate to this URL. And it's a little bit slow on my end right now. Let's hope it picks up. Alright, so here are my projects. And you can see I have a lot of projects already. But for this, let's start with a completely blank project. So I'm going to go to New Project up in the upper right hand corner. You can see, of course, I've been working mostly on bridges so far. So I'm going to New Project. I'm going to give it a title, Testing Bridges, for example. You can give it a description. This is just demo. And then you have to choose a category for some reason. I'm always going for, where is it? Engineering services. I think that applies the most. All right, and since this is a free account, you kind of have to create a public project, which is fine. We're not doing anything secret. All right, so I'm going to create this empty project. I'm afraid it's going to take a while again. All right, here's testing bridges. Now we can open that up. And it's going to load the workbench where we can do all this setup for a simulation run. The run itself, as I said, it will not run on your personal machine. This laptop I'm running it on, as you can see, it's not the fastest as well. So it would take a lot of time to run complicated calculations like this locally on your machine. With Simscale, you just run it on their server, the actual calculation. In that way, it doesn't take forever. And you can also have a lot of calculations running in parallel. There's multiple advantages to it. Alright, so I open an empty project, and the first thing that it wants from me is a file, geometry. We need some form of geometry to run calculations above. So I'm just going to go to import from computer, which is, if I have a file, I can, with this video, I'm going to publish the file I use here, which is just some STL of a bridge, nothing special. If you use Onshape, for example, you can also import directly from there. Alright, so I should have a bridge testing folder here, and there's just a Steg is German for bridge. Maybe I should rename that to make it universally understood. Alright, so we have a bridge.stl in this case. This supports a lot of different formats in software. They give you some information here. So the STL format is the most common one, the one you will probably meet if you get a file from someone or somewhere. It is not necessarily the best for this. I'm just showing it with an STL file because I would expect that that's what most people will see in reality. But for example, importing step files from Fusion, exporting from Fusion step files and importing them here is a little bit lighter on the machine, and there's some different advantages, which I'm not going to go into here, but STL is one of the options. We're going to use it today. With that, I'm not saying it's the only and the best option. There are better options out there. All right, for now, for this bridge problem, it's good enough. So we have one bridge STL. I'm going to import that into this object, and as you can see, it's uploading it to the servers that Simscale is running. All right, and then we can also already see the geometry that we have. And here's the first snag. Maybe that's good. I'm not going to rerun it because this will probably happen to a lot of people. What I just did there seemed to make a lot of sense, right? Now, if we look at this scale, it doesn't. So this would be 20 meters between these 2 points. So this bridge is what, like 40 meters wide or something? Something like that. So I made a mistake when importing. So let's delete this for now and re-import it. So I'm going to go to geometry again, import from computer, choose the STL, and this time remember to go into the settings for this STL and set the model units to millimeter. I don't know why the standard here is meters, because I know almost no one who uses meters as the model unit, but yeah, usually we'll have to choose millimeter here. Just make sure to check, is my model roughly the correct size, and I have no setting problem here. Otherwise, of course, you would get very, very different frequencies in mode shapes. The mode shapes would actually be very similar, just at much lower frequencies. Alright, so this makes more sense. 0.02 meters. That seems to make more sense to me. That seems to be a bridge size bridge. Alright, so now we have one geometry in here. And you can see that in the geometries tree up here. So in this drop down you find all the geometry that we have, and we can of course import many more geometries here. Maybe we want to test 10 variations of the same bridge, then we can import 10 variations of this geometry and have them all on the geometries tab here, collected like this. But for here we just want one. So off of this one geometry we can run one simulation now. So we're just going to hit this little plus sign right next to simulation, and then we get a big window with all the options for simulation. There's a lot to do in Simscale. You can do flow simulation, which is quite complicated, heat transfer simulations, very complicated stuff that we don't really need. We want to do a frequency analysis. We want to know how does this object vibrate. So frequency analysis is the case for us. I'm just going to select it over here and then go to create simulation. Alright, that plops up a single, this is one object, one simulation run that is called frequency analysis. I can rename it like this. Maybe I'll name it 1, 1 or something. This is the first run of this geometry, however you want to name it. This is a single object that contains all these settings tabs. So let's go through them one by one. The first one is the geometry that we choose, and it's already chosen the one geometry that I've imported automatically. Simscale is thinking this guy has one geometry. It can't be that complicated. Probably he wants this one. If I had multiple ones, I would get a list here of all the geometries and I could select the correct one. So bridges 1 to 10, for example, I could choose bridge 4 here or whatever. We need to provide some geometry, and that's already provided here. Contacts and connectors we don't need to worry about here because we just have a single geometry that we want to look at. If we were to maybe make a whole violin, then we would need to contact and connect the individual parts of the violin, the top, the ribs, the back together. But in this case, we just have one geometry, so we don't need to go into that really. And element technology is also already set to the standard values, which we are fine with in this case. And all of that is indicated in each case by this little green arrow. The green arrow generally means everything is set so that we can run a simulation. It doesn't tell you necessarily that's the correct setting for the result that we want to do, but technically we can run a simulation and get a result if there's a green arrow or green tick mark for every of these settings. So the next one we can see materials. There we don't have a green tick mark yet, so we need to set material obviously. So I'm going to go to the plus sign again. And here we have some predefined materials. So there's a whole list over here. Aluminium, for example. And if we scroll down, we also find wood. Or we could think, okay, wood, that seems correct. We have a bridge made out of wood, right? But this is a very simplified wood. So as you can see to the right here, we just get one Young's modulus, one Poisson ratio into density, and it's also called an isotropic material. As you know, wood is not an isotropic material, but rather orthotropic, and we need to provide Young's moduli and Poisson ratios in multiple directions, and also share modulus. So this setting could be a start and would give us a rough guess, but for a real bridge, we really need to set orthotropic material properties. It's a kind of a weird one in Simscale. It can do isotropic material properties, but I haven't seen any of the presets here actually use that setting. And if I go through them, none of them do, and they shouldn't, most of them. But it is possible to set it if I have one material imported. So what I will do here now is just use aluminium for now and apply it. Now we have an aluminium setting here, and I can apply it to this STL file. So if I click it and it turns blue, then for now, for the simulation, it thinks that it's made of aluminium, and it's assigning it mathematically these properties. Of course, we want to set real wood properties, and for that we can just go in here and set orthotropic instead of isotropic. The setting is here, you can use it, but it's not in the defaults. So if you just look at the defaults, you might think it can't do it, but it actually can. So this is the correct directional dependency setting now. We have orthotropic. Now we just need to enter values for these 9 constants into density. How to get the correct values for, maybe you have a piece of wood and you cut a bridge from it and you want to know how will it turn out. Getting those values is a different story, and I'm not going to cover that here, but I'll provide some documentation on that and links, and it's not hard to do, and you don't need any special equipment to get values for these. They will always be kind of a guess. Getting very, very accurate measurements, yes, that's a lab thing, but in the workshop or whatever, you can get a good enough guess, and we've shown that in reality as well also. I'm going to plug some values that I've measured for the wood I have in here. I'm probably going to cut the video here because it's going to take me a few minutes. Alright, so I've now added correct material properties for the piece of maple that I had available to cut a bridge. I'm going to therefore name it maple, the material that I'm using. So we have the material maple applied to our object right now. Of course, if you're doing this, you can copy these values if you want to. Of course, they're not going to reflect the wood that you might have available. They're just a good guess for a maple wood, if you just want to play around with this for now. In reality, if you want to make a real bridge, yes, you have to get material properties for the wood that you have in a more complicated way, but as I said, it's not too hard to do. Alright, so next green tick mark achieved here, going down the list. The next one is boundary condition. And here we're going to simplify just a little bit, as I'm showing in the other video with the actual real life measurement. We're clamping the bridge somewhere here around the foot. So what we would have to do is create a small face that represents the contact surface with the vise and clamp that position here. I'm not going to do that here. I'm just going to simplify a little bit. We are assuming that the vise is so much heavier than the bridge and clamped down to the table maybe as well, that we can assume every point that is clamped by the vise to be actually fixed in space. It will not move at all. There's no resonance there that concerns us at all. So we're going to give a fixed support here. And here it tells us already we need to decide which faces of the object are to be fixed. So as I said, if we want to really define it how we do it in real life in the vise, then we'd have to define a small face here that represents the clamping surface, I have not done that in this 3D file. You would have to do it in your 3D design. And we've seen in real life measurements that this moves the frequencies by about 200 Hz or something like that. In this case, we're just going to simplify a little bit by clamping these faces. These are easily accessible to us. Yes, we cannot represent this measurement really well in real life, but since we know it just pushes up the frequencies by 200 Hz, we still can get relative comparisons. Alright, so now we've set a fixed support boundary condition for these two faces, and the tick mark turned green. So this can now return results that make sense in a simulation run. The next green tick marks are already set again. Under numerics and simulation control, it is using defaults, and those are fine for this quick tutorial as well. So we're going to leave it at that. Result control as well. Here you can choose what results you want to have, and it has defaulted to displacement, which is correct. You just want to see the displacement, and some of the solution fields are not available anyways if you have just a free license like we have here. So there we can't really do much more anyways, and we really don't want to. Displacement is fine for us. So last thing we have to do is actually create a mesh. So this is a 3D file. So it is a 3D geometry, but for it to be calculated in an FEM, it needs to be meshed, and that means creating a lot of small shapes that make up the surfaces of the object and describe the volume. For this we have some basic starting settings which are generally fine for a lot of stuff, but I found that for bridges like this we really want to fine-tune just a little bit. This is a very simplified approach to it here that Simscale is using, which is good. We just want to run something. We don't want to have the finest control about it. You can go very much a lot deeper into this, but here it's relatively simple. We're just going to set fineness to 6. They just have a calculation for that, what they do, define as fineness. We don't have to think too much about that. And then on advanced settings, we want to set the small feature suppression to something like 0.05 millimeters. Make sure to go to millimeters. If you go to meters, it doesn't do anything. So that means if it wants to describe something very fine in here, let's say this edge here, it wants to define, the software could algorithmically run into using a lot of very small parts to describe that. We don't need that at all to describe this bridge. So we're just going to put a limit on that. The smallest feature needs to be still larger than 0.05 millimeters. And this makes our whole mesh much easier to calculate and then to calculate with, and it doesn't lose us anything in the results. So I'm going to go to generate, and it's going to start generating a mesh for this object. And here you can also see what I was talking about earlier. So it's showing you the runtime of this meshing operation so far. Of course, it's 0 minutes right now. And then it's also translating that into core hours, which is basically the currency of Simscale. So as I said, you start with a few thousand core hours, and this really doesn't take long. So you can do a lot of simple simulations like this, even on the free license. I believe the paid license is not too expensive either, but for stuff like this, you really don't need it. Alright, I'm probably going to cut the video here again, and then also report how long did it take. Usually it takes 2 to 3 minutes or something. Alright, so we just finished meshing this part, and you can see what the mesh looks like here. And you can see what I was talking about earlier was kind of wrong. This area is not really a problem. But if you look at areas like this with a small radius, that wants to use very small features. And if we didn't put this small feature suppression on there, then it would use a lot of small features to describe something that ultimately doesn't really matter much. Alright, so this is our guess of the bridge geometry, of course. If you set things like these, so if you go to coarser settings, for example, as well, this is always a representation of the bridge, not necessarily exactly the same. Usually the small errors that we make here don't really affect the outcome in any measurable way or in a in a way that is so small that we cannot even measure it in real life. But still, of course, this has to be taken into account. If you go to very coarse settings here, and if you were to imagine I set the small feature separation to 5 millimeters or something, then of course it wouldn't work at all. So these settings need to be kind of dialed in for your object. And for that, usually what you would do is an iterative analysis. So you start with your bridge, and maybe you start with relatively rough settings, and then you create finer and finer meshes until the result doesn't really change at all anymore. And there you find an optimum where you have a fine enough but not too fine setting for your mesh. And that's what I've done before, so that's how I came up with these settings, which are very, very simple here, of course. For the bridge, and generally for violin bridge sized objects, you should be able to use these settings and get pretty good results. Alright, so this is the basis for the calculation, and we're going to do that now. So simulation runs. Again, you just go to the little plus, and then you can type in a name. Let's name this 1 as well. And it also gives you an estimate of how long will it take. By the way, the meshing took about 2 minutes. Now the actual simulation, it's saying it should take about 0 to 9 minutes, which my guess would be that it takes like 3 minutes or something. So it's relatively fast. And you can run multiple simulations at a time. So if I were to, as I said earlier, evaluate variations of my bridge geometry, I could run all of these in parallel, and then while I'm setting up one run, another finishes already, so it's a very efficient workflow. One thing you will see up here, it says exceeded community plan limit of 10 simulation runs. So you have 10 simulation runs in the beginning where you have basically all the features of the full Simscale available to you, and after the 10th run you lose some features. Those features are really not that important to us. It says numerical results are not available, which is kind of true. You get some of the analysis that you cannot see in here, but you can still download, as I will show later, a CSV file with all the results, all the numerical results that you would want. So it's not really a limitation for our purposes, I would think. Alright, so I'm going to start again and probably do a cut here again, as this will take a few minutes. Alright, so we finished once again. 2 minutes for the simulation run. It also varies a little bit. Sometimes the same simulation seems to take 5 minutes that took 2 before. So this doesn't tell us too much, but about this time it doesn't take very, very long. Alright, so now it just says finished, and we have a creation time and an end time. The actual results of it you can find in these tabs below run 1. So it preserves all the settings that we had for the run. So I'm just going to open this up, and here a little bit grayed out. You can still find for later reference all the settings that were used for the simulation run. So of course which geometry was used might be important, and also which material properties you used and where the boundary conditions were set. Just out of interest, if you run into this, I ran this run like 2 weeks ago and I forgot which settings I used, you can always find these in here under settings. And then the first thing we're going to do here is go to solution fields. Click that, and it's going to load it again a little bit. And there we can actually see the nice colorful shapes and the numerical results that you can find here under tables. While it's loading, maybe I can open that up. You have the actual table with all the frequencies and displacements and modal masses in there as a table, and you can download this as a CSV file. So that's what I meant earlier when I said the numerical results that I would want really are all there, even with the free version and even after running out of the 10 trial runs. This part with the solution field, of course, takes a little bit more bandwidth to load because it's loading actual animations, and those have a little bit higher content. All right, so now we get an animation. This is of course just a still, but up here I could go to animation and then actually run it, which I'm not going to do now because it's probably going to load for a while, but you can try that. And to the right here we can switch through the frequencies. So it found one eigenfrequency of the bridge at 6,999 Hertz, and then the next one down the list is at 6,600 Hertz, and it looks like this. And in this way you can go through it. And for example, maybe here we'll find the rocking frequency, maybe. Yeah, this looks like a rocking frequency of the bridge. Oops, I went one too far, I guess. Yeah, this looks like the rocking. Oh no, it's actually out of plane. It's a mixture, I guess. Of course, the results of this run are not really that important. I'm just showing you here you can find them and look at them in a more qualitative way, I guess. You can just see what is happening, and there's not really you get the number, of course, of the frequency, but not that much actual information content is actually in the modal data table, of course. The first mode should be the forwards and backwards sway of the bridge, and that's what it looks like as well. Maybe I'll try to run one animation. Let's see how my internet speed keeps up with this. So I just clicked on animation up here, and so far nothing has changed. Once I hit this play button, it will show me the individual steps of the animation, and those usually take a little bit of time to load. You can see this blue bar up here is advancing slowly. Each tick basically is one step, as you can see. And once it has loaded all of them, it will actually run it smoothly. So let's wait for that. In the meantime, as you saw, the simulation itself took 2 minutes, and the meshing, if I remember correctly, 3 or 2 minutes. So about 5 minutes of actual calculation time. You can imagine with a few thousand core hours being available for free, you can run forever on a free account, and of course you can just create a new account once you run out. Alright, so this is what the first frequency of this bridge would look like, and it's at 653.4 Hertz in the simulation. 2 points to consider when comparing results from here to real life. Here the boundary condition, as I said, is a little bit simplified. We just claimed these bottom surfaces, which you're probably not doing in real life. The material properties can be off a little bit. We're just guessing for the whole object, of course. And there's some error there. And then in the real life tests that we've done so far in Vilfava, we also found that overall, still when considering all these variables, the real life results were always at slightly higher frequencies than the simulated results. So if you find, oh, I'm actually predicting 3000 Hertz and measuring 3200, don't be too worried. We measured the same. We're looking into why is that the case. We still don't know as of yet. Alright, so here you would have a list with all the frequencies that I found. Maybe 6.6 could be a bouncing mode, and we can look at that quickly. Nope, it's an arm swaying mode. 5.6. Yeah, that looks like bouncing mode. I'm not going to let it load this time. It takes too long. You see what you can do with this. Alright, the last thing would be to look at the actual numbers. So if you go to tables and modal data to the left hand side here, you will get a table with the modes that it found, frequencies, and then the effective modal masses, which I'm not going to talk too much about here. Just remember, if you were at the Vilfava workshop, we looked at the modal effective mass from the actual measurement as well. That I've not looked into too much in this tutorial here. I'm just showing the basics. But yeah, the answers to that could be found in here as well. Alright, so that's Simscale, doing a relatively simple run of a bridge. And of course, this is just an introduction. I've not covered all the bases probably, but I hope you can follow along a little bit and get into Simscale like this. Alright, thank you.